Hello everyone, hello Science Alliance, Lara here. This is lesson 5 of infection and response. We've not got long to go. We have done a lot about infection, about pathogens, germs basically, teeny tiny living things, bacteria, viruses, which are maybe not alive, fungus and stuff that infects our bodies. Next week we're going to learn about how we respond to that, like the white blood cells, vaccinations, that kind of thing. But there's a very important bit in the middle that we just never think about, but we're going to think about it today, okay? So the first thing I thought we'd do, because it's a good activity that I got from Science Buddies, who are amazing website, is an activity to think about the size of these things. Because at the moment we're just kind of saying pathogens like they're all sort of the same thing. They're really not. If you've got a piece of paper with you, which you should have, there's a lesson, isn't it? And a ruler, do me a favour, have a look at the thickness of your piece of paper. Have a look at the thickness and try and measure it with your ruler. So it's just normal printer paper that I've got. How thick is your piece of paper? Give it a measure. You can't do it, can you? You can't do it. At least you do a very shoddy job. Why is this? It has to do with units of measurement. So if I was measuring the width of this room, I would probably use meters. Yeah, maybe I'd use centimeters at the end, but generally it's quite a big room, so I could use quite a big unit, the meter. If you were measuring the length of a pencil, it wouldn't make any sense to use meters, would it? You'd use centimeters because they're smaller, 100 centimeters in a meter. If you were measuring, you could do this. Take your little finger with your ruler, try and measure the width of your little finger. There's no point using centimeters because you just end up with a result like a centimeter and a bit. You would use millimeters, wouldn't you? So 1 centimeter is broken up into millimeters, and this is not rocket science, it will get more complicated than this. 1 centimeter is broken up into 10 millimeters, and you would probably use that to measure the width of your finger, because then you could get a more precise result. Instead of saying 1 centimeter and a bit, you could say, I don't know, what's that, like 17 millimeters. But your ruler is much smaller. Your piece of paper, the thickness of it is much smaller than a millimeter, isn't it? So we need to use a new unit of measurement, which to us might sound quite weird. Some may say scary. To scientists who are dealing with very small things, it's just totally normal. You would use something called the micrometer. Micrometer. Careful of the spelling. If you're American, then you can put an ER on the end. In England, we only use the word meter with an ER on the end, like be a kind of like sort of machine, like reading the electricity meter. So if you're doing British English, do an R and an E in the end. So the micrometer is just a really small unit of measurement. 1 millimeter has got 1,000 micrometers in it. The symbol for micro is gorgeous. It's this little mu symbol. I don't know whether it's Greek or Latin, but anyway, it's cute, isn't it? Like a posh U. So micrometer. 10,000 micrometers is 1 millimeter. I was racking my brains for something small that we could see that could kind of help us get this into our brains. And then I had a brainwave, right? Look at your fingerprint. You know how everyone's fingerprint is unique and it's all made of little swirls? Well, your fingerprint is made of like dips and ridges. Little dips and little kind of hills called ridges. If you have a really close look at your fingerprint, the distance between 2 ridges, like just 2 lines next to each other, you could measure that in micrometers quite easily. So here's a massive fingerprint. I'm going to close up even more, which some people found quite creepy yesterday. This distance between 2 ridges is 0.5 millimeters, half a millimeter. So I've just told you that 1 millimeter is 1,000 micrometers. So what's the width from ridge to ridge on your fingerprint in micrometers then? It's not a great question, is it? It's just you can if you can, and if you can't, you can't. But I'll give you 5 seconds. What's the width from ridge to ridge in micrometers if it's half a millimeter wide and there's 1,000 micrometers in a millimeter? 3, 2, 1. It's 500, isn't it? Well done if you got that. So yeah, that might help us to visualize it. Have a look at your fingertip. The distance between those lines there, 500 micrometers. Okay, so what I want to do now, we're going to make a little poster. So hopefully you've got a piece of paper and on it you can write the size of things times 1,000 if you haven't done already. The size of things and stuff times, sorry, did I say 1,000? Times 10,000 we have to times it by. What we're going to do is pretend that we're going to a world where everything is 10,000 times bigger than it actually is. Look, I will show you that on the screen. Let's pretend we've gone to a world where everything is 10,000 times bigger. I would like you please now to cut a piece of wool or string or cotton, whatever you've got, to about 1 metre long while I show you a scale model. So most of you probably won't have metre rulers. I haven't either. You'll just have to hold the string against the ruler and measure 30 centimetres and then hold it in your fingers and measure another 30 centimetres and then measure another 30 centimetres and then hold it in your fingers one more time and measure an extra 10 centimetres because that will make 100 centimetres. So get 100 centimetres of string. Yes, what we're sort of basically doing is making a scale model. A very popular scale model that I use all the time is this one. Google Maps. Oh, Google Maps, how I love you. But if you look right into this corner where you might not have looked before, you can see, right, there's a line and it says 1 kilometre. So this is a map of York where I live. And what this is telling me is, oh, you can see all my favourite places. Look, you can see that I love pizza and donuts. So this line here is telling me that this distance on my map is equal to 1 kilometre, right? This line equals 1 kilometre. If I zoom out, what's going to happen to that number? Is it going to go up or is it going to go down? At the moment, that length of line equals 1 kilometre. If I zoom out, is it going to equal more kilometres or fewer kilometres? Decide. Let's see. So I'm zooming out. It's gone up, hasn't it? Look, it's doubled. So it's pretty much the same length of line, but now it's equal to 2 kilometres. And if I zoom out and out and out, this scale model is pretending that everything is much smaller than it actually is, isn't it? And the more I zoom out, then the smaller everything gets. Do you want me to zoom all the way? I know you do. Yeah, I did as well. How far? Look at that. Till eventually you get the whole of planet Earth. And that line is now equal to 2,000 kilometres. So we're doing the opposite of Google Maps. We are pretending that everything around us is much, much bigger than it actually is. So have you cut your metre of string? That metre of string now represents something in our new world, okay? What do you think it represents? What do you think that metre of string, everything in the room, look around you, right? So the ceiling, the windows, you know, the fridge or whatever, that's all now so big, 10,000 times bigger, that it's just kind of blurry shapes in the sky. What would we actually see around us if everything in our room was 10,000 times bigger? Well, the thickness of a piece of paper would be 1 metre, the length of string that you've just cut. So if you want to like balance that next to you, then you can imagine that we are now in a world where a piece of paper laying on its side comes up to 1 metre to your body, all right? It's pretty good, isn't it? So what else are we going to see in this world, right? Imagine you're now standing next to a piece of paper, it's 1 metre thick. What are you going to see around you? Well, I'm going to get you to cut 4 different lengths of string. One of them is impossible, you're just going to have to do a dot. But cut 4 different lengths of string, and I want you to try and match up what this string could be in our new everything is amazing world. Here we go. So we're imagining things are 10,000 times bigger than they actually are. Can you cut string to these lengths, please, and stick them onto your sheet? 10 millimetres, 0.15 millimetres. Is it possible? Just do a speck. 20 millimetres and 80 millimetres. Are you okay with the fact that 80 millimetres is just 8 centimetres? So you want an 8 centimetre piece of string, a 20 centimetre piece of string, a 1 centimetre piece of string, and a 0.15 millimetre piece of string. It's less than 1/10 of a millimetre, totally impossible. Stick them on your piece of paper, and then tell me what you think those pieces of string represent in our new massive world. So one of them is about the length of a yeast cell, one is the coronavirus, one is an E. coli bacteria, and the other is the width of some spider silk. But which one is which? I'm going to bundle up my A4 piece of paper string. Obviously you can't stick that to your sheet as it is, but you might want to roll it up and stick it to your sheet. And I'll do the others alongside you. And if you get finished, I've said find 2, I think 1 will be enough really. Find 1 tiny thing to measure and try and work out what does it measure in real life and how big would it be in our scale model. If you're using wool that's anything like mine, it's going to be very inaccurate because it's just so fuzzy. But do your best. The relative sizes will still be all right. Okay, I'm going to cut my... Oh, it's not even worth... I'm going to wet my finger and roll my wool into the tiniest dot I can imagine. It's still not going to be anything like small enough. Okay, I have done my cutting, so I'm sticking it to my sheet. You can label the A4 piece of paper if you like, because we know that one already. You might not want to label the others until I've told you the answer. Thickness of A4 paper. I suppose it doesn't really matter how wide I'll put A4 paper. Right. While you're finishing off, I'm going to go and find a tiny thing and measure that. Because this is some good maths practice. I'm going to go to my cupboard where I keep all my seeds. Okay, I have a single mustard seed here. So if you finish, you can be doing the same thing. Find something teeny tiny and see if you can work out how big it is in our model. Okay. How are you getting on? I'll go through the answers to the first one. Oops. And then you can be labelling it if you would like to. So, let's start with the biggest one, okay? So if you've cut a piece of string or wool that was 8 centimetres long, what do you think that represents? Is that going to be a yeast cell in this new massive world, coronavirus, E. coli bacteria, or width of a spider silk? The answer is... it is the width of spider silk. Spider silk, very thin, eh? A piece of A4 paper is a metre in this world, and spider silk is only 8 centimetres. It's hard to believe. But I trust science buddies, and I do. Right, the smallest one. I think you might have got this if you've been listening in previous lessons. The smallest one, this tiny speck that is impossible to cut, is coronavirus, or any kind of virus really, very, very small. Coronavirus and viruses we often measure in nanometers actually, which are even smaller than micrometers. And then there's not that much difference between yeast and bacteria, but generally speaking, yeast are bigger. So something about 2 centimetres big in our world is going to be a yeast cell. Yeast, fungus is kind of between sort of 2 and 6 micrometers, I think, whereas bacteria tend to be smaller, between 1 and 2 micrometers. So E. coli bacteria in our new world would be 1 centimetre wide, which is really quite horrifying. Let's flip you around now, and we'll go through it together. So hopefully you've stuck those things to your sheet and you can label them. So label the big piece of wool as being the thickness of a normal piece of paper. And the teeny tiny little one is a virus. The slightly bigger one is a bacteria. I guess if it's one bacteria, I should say bacterium. Oh no, I'm writing backwards. I don't need to write backwards. It's YouTube, sorry. Very confusing because on Facebook I usually write backwards. A lot easier to write bacterium forwards. Bacterium. The bigger thing is yeast. And the massive thing is spider silk width. Spider silk width. So it's quite useful, isn't it? Because it really gives you an idea of how viruses kind of are in a league of their own. Like if you zoom right in, there's a huge difference, pardon the pun, between a virus and a yeast cell, for example, even though we say they're all pathogens. I was trying to look up whether like viruses were more deadly because they were small. I found some research that said that they'd seen a pattern that the smaller a virus was, like the more frequent the outbreak, I think. So in some ways, very small viruses are more problematic than big viruses. But there's just one study. Okay, so I found a mustard seed, which is about 2 millimeters wide. I'm going to show you just for, I don't know, aesthetic reasons, just in case you don't believe me. I've got this mustard seed, okay? It's about 2 centimeters wide. 2 millimeters wide. If it's 2 millimeters wide, how big is it going to be in our model? Well, I find the easiest thing to do is to sort of add zeros and then take them away. I'll show you what I mean. So 2 millimeters. Let's times that by 10,000. So to times it by 10,000, what are we actually doing? We're kind of moving the decimal place, aren't we? So with a 2 millimeters, the decimal place will be just the other side of the 2. If I times it by 10, then I move the decimal place 1 and I get a 0 there. If I times it by, that's times it by 10. If I times it by 100, I have to add 2 zeros. If I times it by 1,000, I have to add 3 zeros. And if I times it by 10,000, I add 4 zeros. So that's quite easy. I know that in my model, my mustard seed is going to be 20,000 millimeters long. But it's not a very useful unit, is it? Like, what's 20,000 millimeters? I can't really picture it. So I just have to divide again. That's the easiest way for me to do it. I've got a number in millimeters, 20,000 millimeters. What's that in meters? Well, there's 10 millimeters in 1 centimeter, yeah? So if I want this number in centimeters, I have to divide it by 10, which means my decimal place has to go back again. So if I put my decimal place there, then I know that my mustard seed in my model is 2,000 centimetres, but there's 100 centimetres in a metre. So I can divide this number 2,000 by 100, and that gives me my answer in metres. So I'll just move my decimal place, 10 100, and if I divide that number by 100 to get the answer in metres, it's 20 metres. So in our new world, my mustard seed is, imagine that, standing next to a metre high piece of paper and seeing a mustard seed that was like 20 metres into the air. Terrifying. I think we better leave this world and do some stuff about defences. I did say that that's what we were going to do. Right. So, oh yeah, first, just before we go then, to come back to this fingerprint idea. We have learned that the distance between the ridges on your finger is 500 micrometers, and we've learned that a bacterium is 1 micrometer wide. So just have a look at your finger again. You'd fit 500 bacteria into that space between the ridges of your finger. Isn't that amazing? Amazing. Okay, so I said, yes, your body is doing loads of things, and they're so obvious, we just don't think about it. So imagine a pathogen in the air, okay? It's a germ, it's going to cause us disease. Let's say if it got to your lungs, then it would make you very ill. Whatever this pathogen is, doesn't matter. If it gets to your lungs, it'll make you ill. What is your body doing to stop a pathogen getting to your lungs? Loads of super obvious things. I'm just going to give you like 15-20 seconds to write down as many ways that you can think of that the body is stopping that pathogen from getting in. Try and go really obvious. Here's a picture of a sort of cut up human body to inspire you. How does the human body stop germs getting in? Go on then, 30 seconds to write down all your ideas, but you've had 10 seconds already. Grabbing some visuals from my washing up pile. How have you got on? I'll flip you back around again and give you a few more clues. So hopefully you got a few. We tend to separate our defences, how we stop germs getting into our body, into two groups. We call them physical barriers and chemical barriers. So the one that always came up in that answer when people were watching on Facebook was everyone would always say, nose hairs! Yes, nose hairs are one of the ways that pathogens would not get to your lungs. Nose hairs would be a physical barrier. So for example, I don't know what this is. Here's a gross jammy spoon from my washing up. If I want to get rid of the jam on my spoon, there's two things I can do, right? I can just get some kind of Brillo pad or sponge and just rub it in some water, okay? And physically get rid of the jam with my force, just push it off, or, you know, yeah, it's a physical thing, right? Or I can, say, soak it in some washing up liquid, which would be getting rid of it in a chemical way. So chemical doesn't always mean chemical reaction, right? It just means sort of chemicals are involved. Chemicals are doing the job. So you've got physical barriers, which would be nose hairs, like physically stopping the pathogens from getting in. But there's some chemical barriers as well. So for example, the one you probably won't get is that your skin is slightly acidic. So pathogens don't last long on your skin because of the acid. So there you go. I've given you some clues. Another 20 seconds. If you've got some barriers written down already, can you split them into which ones you think are physical and which ones are chemical? Or you could write down the ones that I've just told you, if you can remember them. And then I'll go through them. 20 seconds. Think of as many as you can. Can't remember how many I've got listed down. Maybe 8? Ten seconds. If you're thinking, why are you rushing us? I was just trained this way. It's called pacing. I was not good at it. It's like, you've got to be faster, you've got to be faster. Right, should we go through the answers then? So let's start with the chemical barriers. Tears and saliva. Yeah, true facts. So obviously your skin is a massive physical barrier, right? Your skin is the most important physical barrier. It would be quite easy, wouldn't it, for a germ to get to your lungs if your skin wasn't there. Not worth thinking about too much. So the chemical barriers tend to be in the areas where you don't have skin. Obviously, eyes are just holes in your face. So in order for pathogens to not get in there and cause infection, your tears and your saliva as well in your mouth they've evolved to have enzymes in them. Enzymes are chemicals, and there's this specific chemical called lysozymes, which is doing an absolutely fantastic job. So you remember me showing you ages ago, I think in the bacteria lesson, how bacteria make their how bacteria build their cell walls. Do you remember that? And we looked very briefly at how antibiotics work. So I showed you, just quickly doing it now, that there are little proteins that the bacteria kind of build their cell walls with, right? Like this. Bacteria build their cell walls by just attaching loads of these proteins together in a kind of like gross necklace bracelet type arrangement like this. Okay, so that's a bacteria cell wall. And we looked at briefly how penicillin, certainly the first bacteria discovered, works, is that it kind of gets into the cell wall of the bacteria and weakens it. So when the bacteria is in your body, this particle causes it to kind of, well, we thought it exploded, destroying the bacteria. These lysozymes, these enzymes, chemicals that are in our saliva, in our tears, as well as in various other bits of our body, they kind of work in the same way. So what they do is they sort of, they attack the cell wall of the bacteria until it opens up. It turns out, scientists have only very recently discovered that some bacteria can live without their cell walls. So the cell wall breaks, the bacteria comes out, they're called like L something bacteria, but they can survive. They're weakened, but they do survive. And this is one of the reasons why people become immune to antibiotics, right? So maybe you get ill, you take antibiotics, you get better, but then you get ill again and the antibiotics don't work. It's because your lysozymes, your enzymes in your body have made this bacteria burst open, but the bacteria is still alive, and then the antibiotic comes along and it's like, where? It can't work because it destroys cell walls, and there is no cell wall. Terrifying stuff, eh? Right, moving on. Stomach acid is also a chemical barrier. You might have got that because I showed you that quote from BBC Bite Size that we'll look at in a sec. And mucus is also a chemical barrier. Well done if you got that. And like I say, sweat is acidic, so you can put that on your list. Physical barriers, cilia. And we've got I've put tiny hairs in inverted commas. The hairs in your nose are obviously actually hairs. You don't need to touch them. They're hairs, okay? But there are these things called cilia. I think I've spelt it wrong on my sheet. I think it's 1L. Cilia are not actually hairs. We tend to call them hair-like cells. They're cells, but they've evolved to basically have a kind of hair-like thing sticking up from it. And they are incredibly useful in our trachea. I'm just going to find you a picture now on the wonderful Wikipedia. So if you put your hand gently on the front of your throat and give it a wiggle up and down, you'll feel lots of rings, yeah? That is your trachea, that tube. All the rings are there, made of cartilage, to stop it collapsing, because air is going in it and out of it. So it's super useful that it doesn't collapse. So that's what all those rings are. If you look inside your trachea, it's just a world of biological wonders. Here we are. Thanks, Wikipedia. Thanks, OpenStax College, for letting me show this. Yeah, here's a cross-section of your trachea, right? So these are the cilia. You see these teeny, tiny, gorgeous little hair-like things lining it. And this is a goblet cell, this pale shape here on the end of this black line. And goblet cells make mucus. So what is happening is, if a pathogen gets into your throat, then the goblet cells make mucus, and they're all sticky, so they sort of stick the pathogens together so they can't get any further. This is all going to come up in a GCSE question at the end of the lesson, by the way. Goblet cells make mucus. Mucus makes the pathogens stick together because it is sticky, and then the cilia waft the pathogens and the mucus out of your throat. And where do they go after that? Well, that's right. You end up swallowing it, don't you? And it goes into your stomach, where everything's fine because the stomach acid is waiting for it and will destroy it. So stomach acid gets rid of any bacteria or pathogens that are living in mucus that you might have swallowed because they've come from your trachea, and also like any pathogens, well, not all of them obviously, because otherwise you wouldn't get food poisoning, but pathogens that are on food. Your stomach acid gets rid of those. Let's go through the last of the physical barriers. Your skin, as we've said, and grazes as well. Grazes are a fabulous physical barrier. I won't go into it too much because this isn't a lesson on blood, but your blood has got white blood cells in it, which attack germs. We'll look at those next week. It's got red blood cells in it, which carry blood around your body, also very useful. It's also got these things called platelets in. I'm going to spell them possibly incorrectly on the board. I think it's like that. Is it platelets or is there an E? Anyway, platelets are what clot your blood. So if your skin gets cut, that's bad, isn't it? Because pathogens can get in. It could get infected. So the platelets in your blood very quickly form a scab, which is a physical barrier, yeah? Okay, so I showed you this paragraph from BBC Bite Size and I asked you what was wrong with it. There's one major thing that is wrong with it, and I'm sure it's just a typo. Stomach acid does not break down food. It's part of the body's non-specific first line of defence. It is hydrochloric acid, and while it does us no harm, it is strong enough to kill any pathogens that have been caught in the mucus in the airways. So hopefully you're understanding what this means now, right? Germs get caught in the mucus, in the airways, the trachea, the breathing tube, or they're on food, or indeed in water. Stomach acid is a chemical barrier against infection. So BBC Bite Size is right that all these different barriers we've talked about are called our non-specific defences, because they're not targeting any pathogen in particular. You know, we'll look at how white blood cells target certain germs, whereas this is just keeping all general germs out. Stomach acid does not break down food. Yes, it does, BBC Bite Size. This is just a typo. I'm sure it should say stomach acid does not only break down food, because it does break down food. And other people say in last lesson, does it kill all pathogens? Well, I don't think so. Alice was saying we literally just heard about a bacteria that can neutralise stomach acid. There's a bacteria, isn't there, that neutralises stomach acid and then burrows into the lining of stomachs, and that's what causes a stomach ulcer. Just such a lovely lesson, isn't it? From start to end, these ones. Yes, so, and even the idea of hydrochloric acid doing us no harm, like acid reflux is when acid gets out of the stomach and does cause harm. So anyway, thank you for criticising BBC Bite Size with me. Still love it, but best to check everything twice if you read something that you're not sure of. Okay, I've got 3 questions for you to check how much you have understood this lesson, and then I'll give you the GCSE question, all right, which is a bit of a doozy today. I should first of all tell you how I do this for a living. So if you are enjoying these all ages homework lessons, I also do an all ages Lego Storytime show every week, and I do an IGCSE physics lesson every week that you are most welcome to come to. I can only do them. I have no other source of income. This is only my job because enough people are supporting me with £5 a month. So if you go to my About section, which is somewhere on this page, and you click the link, it'll take you to this website where you can support me with £5 a month, and I'll even send you nice things to say thanks. I'll send you rainbow glasses that make you see rainbows, they're amazing, and I'll send you a description of how they work that I wrote, and I'll send you Theatre of Science magazine. The Christmas one's really nearly out. I won't bother going on about it because you might be watching this in May on catch-up, and that would be boring, but yeah, please get Theatre of Science magazine, it's really good, but children, not you, only adults. Right. Question 1, which is smaller? Badly worded, isn't it? I should have said which is smallest. Which is smallest? Bacteria, yeast, or virus? Which is smallest? Bacteria, yeast, or virus? 5, 4, 3, 2, 1. The answer is the virus is the smallest one. That was a little speck on our poster. This might be tricky. How many micrometers in 1 millimeter? How many micrometers are there in 1 millimeter? 5, 4, 3, 2, 1. It's 1,000. I thought you might say 10,000 because we were pretending everything in our world was 10,000 times bigger. But there are 1,000 micrometers in a millimeter. And the last question, which of these is a chemical barrier? Which of these is a chemical barrier? Stomach acid, skin, or cilia? Actually, this is kind of, you can answer this 2 ways, can you? If you're looking at this question and thinking, yeah, Lara, this isn't a great question, well done, 10 bonus points to you, because I was saying the answer was stomach acid, but I have just said, haven't I, that skin is slightly acidic, so maybe skin is both, I don't know. Anyway, how we go at this GCSE question? This is a good one, we don't usually do these. It's 1 sentence and you get 6 marks, so have a look. Describe how the human body prevents pathogens from entering. So only question, describe how the human body prevents pathogens from entering. And you get 6 marks. How much of what I've just said do you remember? But it's also not about remembering. This is why we practice GCSE questions, because they're so tricksy. Be really obvious. That's my only clue. Just be incredibly obvious. Pretend the examiner doesn't know anything at all. I'm trying to do it with you in my head. It's quite hard, actually, isn't it? It's hard not to get distracted and to remember all the bits. Oh, yeah. I'll give you another 20 seconds because you're writing and I'm only thinking, and then I'll put the answers up. Be really obvious, okay? I'll give you a clue. You get a mark for stomach acid, but you'll also get another mark for writing something really obvious about stomach acid. Ten seconds. Okay, you ready for the mark scheme? Because I think this was tricky. Here we go. So obviously this is GCSE, so some of the stuff we haven't been through, but if it's underlined on a GCSE mark scheme, that means you have to have said it to get a mark. So you might have written about your skin. If you wrote just skin, you don't get a mark. You have to have written skin acts as a barrier, and that would be 1 mark. And if you mentioned scabs, then you got a mark. Scabs form over cuts, or scabs form a barrier. So just the word scab on its own wasn't enough, but if you said cuts get scab over, that would be fine, that would be a mark. And if you remembered that platelets were involved, you basically do get a mark for just saying platelets in the same sentence as scabs. Stomach contains acid. If it's in brackets, it means you don't have to have said it. So that's quite good, isn't it? If you just said stomach acid, you get a mark. Look, you get another mark for saying that the stomach acid kills bacteria. So that's it's quite obvious, isn't it? But you have to have said it. So you get a mark for stomach acid and a mark for kills bacteria. And another mark for saying that if the bacteria is in the food or in swallowed mucus. That's quite a nice way to get 3 marks. If you said your eyes make tears, I think if you've just written tears, that would be fine, that's a mark. And if you remembered the word enzymes, those chemicals that kill bacteria, you get another mark. So well done. And if you mentioned that the trachea makes mucus, that's a mark. Mucus is sticky is another mark. Mucus traps bacteria is another mark, and mucus gets carried away by cilia is yet another mark. So there were quite a lot of marks there up for grabs there at GCSE. I'm going to hang on there for 5 seconds for you to note down as many answers as you like. Mark your work, right? And be brutal. It's sort of better learning. It doesn't matter, is it? No one's looking at it. Better learning to be really fussy and mark yourself very harshly, and then you learn better for next time. Right, that is the end of the lesson, except I'm going to go over to my Facebook homepage where I've put a post saying, I'm on YouTube, say hello here if you want to. This is nice because I know there's at least 1 comment because Jack and Mauve said hello already. And Suze, shouldn't forget Suze. I'm sure Suze is working very hard as well. So let's go and see if anyone's left me any comments, and then I will go because I've got to, oh yeah, look, oh, is it Hannah and Abby? Or is it Kim saying, sorry, we can't make it today? Let's have a look. Sorry, that was a real... Oh, we have made it today! Yay! Amazing! Oh no, there's loads of comments. That usually means people saying, I can't find it. Oh no, it's just Lucy. Answering questions. Well done. And Hannah and Abby, would you get marks for saying the body has physical and chemical barriers? And then giving examples of them. Oh yeah, good question. Would you get a mark for saying the body has chemical and physical barriers? No, it wouldn't have been enough. No, you would have had to have, if you'd said it has chemical and physical barriers, and then you'd mentioned skin, then that would have been 1 mark. Yeah. Oh, so nice. There's loads of comments, and I haven't read a comment yet of people just going, I can't find you. Let's have a look. Is Chloe here? Oh, no way, Robin and Hissy are here. Robin and Hissy, I was thinking of you. Hissy is Robin's pet snake, and the story time today, if you haven't seen it already, Robin, there are some dead snakes in the beginning. I thought I had to say, don't bring Hissy. Just get them in a corner, like reading a comic or something, okay? Because they're going to be upset by story time this week. Robin and Hissy, your dad's sick. We think it's a virus and not bacteria. Oh no, oh no. Lucy is here on time, and it's Tom, just super excited about Advent. Yeah, I know, Tom, I'm warming up, can you tell? This is like my pre-Christmas jumper. It's like touching on Christmas. Maybe every day I should put a new Christmas decoration or some sort of Christmassy thing in the background. Oh, that's a good challenge, isn't it? And there's Bella. Oh, hello, Bella. And Ophelia and Imogen, hiya, brilliant. Oh, and there's Abby saying stomach acid does cause harm to your body if it gets out of your stomach. Exactly, because your stomach is the only organ designed to withstand it. Exactly, BBC Bite Size. Have a look at yourself. Ah, how lovely to read all your comments, especially with them being such good questions as well. Okay, you lot, I'm going to go because I've actually got an hour for lunch, and then I'm going to do my show with a Lego Storytime on YouTube at 2 p.m. And then I'll see you next week when I've had quite a lot of feedback that suggests you would appreciate a kind of recap, dare I say, test lesson? I mean, tests can be a bit sort of horrible and scary, can't they, in school? But actually, if they're just a kind of way to quiz yourself to see how much you've learned and then, like, check your understanding, that might be quite good. And since it's Christmas, maybe we can make the very last lesson a kind of test/Christmas quiz. So I think next week will be all the white blood cells and the vaccinations and stuff we haven't covered, and then the week after that will be a kind of recap final test lesson. Right, okay, I'm just faffing now. I'll see you